So I'm going to talk today about this Ellis Semigroup. So it's an algebraic invariant of dynamical systems. It's also known as the enveloping semigroup. It's joint work in continuation with Johannes Kellendonk, who is also at Lyon. So what I'm going to do is I'm going to start with complete basics. There's a slide reminding you all the definitions for semigroups. Then I'll talk about matrix semigroups, which are sort of important for today's talk. Then I'll talk about the Ellis semigroup, sort of enveloping semigroup to define it and sort of give you some basic facts that are good for us today. Then I'll move to substitution shifts or bijective substitutions, which you all probably know. And then I will talk about how Johannes and I prove our results by sort of giving a baby proof for the 2 imors substitution. All right, so I will explicitly compute the Ellis semigroup of the 2 imors substitution. And that will give you an idea of what techniques we use and you know, what there is to be done after. All right. Okay, so the first slide really is the most basic slide. So if you know what a semigroup is, you can sort of ignore this first slide, go get some coffee. So a semigroup is a set with an associative binary operation. And for us, our semigroups are going to be semigroups whose elements are functions from a space into itself. So that's why our operation is where it's composition of functions. So we denote it multiplicatively. Our semigroups never have 0 elements. Sometimes they'll have an identity element and sometimes they won't in today's talk. But the actual Ellis semigroup always has the identity element. So an idempotent is an element satisfying p squared equals p, an element of the semigroup. And you can define ideals the same way that you define ideals for rings. So a set I in my semigroup is a left ideal if it's closed under a multiplication on the left by elements of the semigroup. Okay, right ideal similarly, and bilateral if it's both a left ideal and a right ideal. Okay, so now if you look at just the set of bilateral ideals, you can order them by inclusion, right? So, you know, I is a subset of J. That means that I is less than J. And a minimal ideal with respect to this element, sorry, a minimal ideal is an ideal which is minimal with respect to this order. All right. And an idempotent is minimal if it lives in a minimal ideal. Okay. And so now the kernel of a semigroup is the intersection of all bilateral ideals. It could maybe not exist because the intersection might be empty, but if it's non-empty, that's called the kernel. And a semigroup is simple if it equals its kernel, right? So that's what a simple semigroup is. And now I can ask for something else. I can talk about a completely simple semigroup, right? So completely simple semigroup is a semigroup, which is simple, but which also has minimal idempotence, right? And so Rees so this is a slide about matrix semigroups, and Rees in the 1940s proved a result where he characterized completely simple semigroups, all right? So I'll first tell you about these matrix semigroups, and what Rees showed was that a semigroup is completely simple if and only if it is isomorphic to a matrix semigroup. So what is a matrix semigroup? So you're given a group and you're given 2 non-empty sets, I and lambda. And the idea here is I is going to index your right ideals, lambda is going to index your left ideals, and your semigroup is a disjoint union of groups, which are all isomorphic to this group G. Okay, so you can think of sort of like a rectangle, one side indexed by lambda, the other side indexed by I, and your semigroup is sort of, you split it up into squares and it's a union of all those squares. All of those squares are groups. Okay, okay, but so the semigroup is, the elements of the semigroup are triples in the set I cross G cross lambda, right? If you fix I and lambda and you let G vary, you get one of these groups. Okay. And then there's a multiplication operation that you can perform on elements of this matrix semigroup using what's called a sandwich matrix A. It doesn't really matter, I've written it there, but the point is that with this multiplication operation, you can easily find the idempotence. And the idempotence, for each I and each lambda, you get an idempotent where the central group element comes from your matrix. Okay. All right, so Enrice's theorem in the 1940s is that a semigroup is completely simple, so has an idempotent and is its own kernel, its own minimal bilateral ideal, if and only if it's isomorphic to a matrix semigroup for some group G. Okay, so these semigroups will play a role in what I'm talking about today. And now I'm going to talk about the Ellis semigroup. So I'm going to just define it. So the Ellis semigroup is an algebraic invariant of topological dynamical systems. So what is a topological dynamical system? You've got a space, which is a compact metric space. And so in today's talk, our space is going to be bi-infinite sequences of letters from a finite alphabet A. And then you have usually, I mean, you can have just a continuous map, but today we actually have a homeomorphism on our space T. And so in today's talk, our map is going to be the shift map, okay? And that defines a Z action on my, my space X, okay? And so now the Ellis semigroup of this topological dynamical system XT is going to be the compactification of the Z action in the topology of pointwise convergence on X to the X. So elements of my Ellis semigroup are going to be functions from X to X. And the way you want to think of them is that you can reach such functions by taking limits of the shift map or the transformation T along some subsequence or some net. And topology of pointwise convergence, all that means is that F is the limit of T to the nk if and only if for every point X in your space, F of X is the limit of T to the nk of X. Okay, so I'm going to give you some facts about the Ellis semigroup. So these facts are not sort of trivial, but they're very useful to sort of set the stage, all right? So the first fact is what's called the BFT dichotomy, okay? And what it tells you is that the cardinality of an Ellis semigroup is one of, it can either be quite small, so it's 2 to the aleph naught, and if that happens, your system's called tame. And most of the work that's been done on Ellis semigroups is about tame systems, all right? So examples of tame systems are your space is actually a group and your transformation is a rotation. Okay, so those systems are all tame. So the alternative then is that if it's not a tame system, if it's a non-tame system, the cardinality of the Ellis semigroup is 2 to the power of 2 to the aleph naught. So much, much larger. And that's why there hasn't been much work done in terms of explicitly describing these non-tame systems. And so today's talk is, to our knowledge, the first time we describe such a system, such non-tame systems explicitly. Okay, so that result that I'm talking about is relatively recent, but much older is a result which tells us that our Ellis semigroup, we are guaranteed that we have a kernel, and we're guaranteed that we have idempotence, okay? So this follows from results by Ellis, Nakamura, and Rupert, which say that if, that the Ellis semigroup, if X is a compact space, the Ellis semigroup is a compact semigroup. That follows from compactness. And it's right topological, which means that, you know, if you fix an element in your semigroup G, the map F goes to, F composed with G is continuous, okay? But so we're not really going to use that today, but we will heavily use this result, which tells us we have a kernel and we have idempotence, Okay, and we want to actually figure out what these idempotents are. And so the link between idempotents and dynamical systems, or maybe the link between semigroups, Ellis semigroups, and dynamical systems, is that there's a specific dynamical property that Ellis semigroups sort of grab and really nicely describe, right? So there's a notion of proximality. So 2 points are proximal, 2 points in my space, X and Y are proximal, if you can clobber them with a sequence of powers of the transformation and send them to the same point, right? So since our points are sequences, what I can say then, so 2 sequences, X and Y, are going to be proximal if you shift to the right, you will see in X and Y places where they agree from some index nk on for a large amount of time. Okay, so a specific example, supposing you had 2 points X and Y, which actually agree from some point on, right? So 2 sequences which agree from the 7th index. Okay, so that's actually stronger than proximal. It's called right asymptotic, but proximal is enough. Okay. All right, so the Ellis semigroup captures this dynamic property really nicely. Okay, it says that X and Y are proximal if and only if you can find a minimal idempotent, so a function P, which projects P of X equals P of Y. And another thing is that if T acts minimally, and today our transformations always act minimally, that's the shift, then, and if X and Y are proximal, then you can find a minimal idempotent which sends X to Y and fixes Y. Okay, in fact, and therefore it fixes Y. Okay. So this will come back to proximality in a little while. All right. So to rephrase, we're going to be looking at large Ellis semigroups. Our Ellis semigroups have kernels and they have minimal idempotents. And we're going to try and find these idempotents by finding proximal pairs of elements. Okay, so this is the slide which is about substitutions. I apologize to all of you because probably most of you know this. So we're looking at constant length substitutions, length L. So in this case, the substitution would be a map theta from the alphabet A into words of length L on A. And I can think of my substitution theta as a concatenation of L maps from the alphabet to itself. Okay, so this notation will be important. So theta sub I is a map from A to A, and theta sub I of A tells me what the ith letter of theta of A is. Okay, and theta is bijective if each of these maps is a bijection. Okay, so if you don't know much about bijective substitutions, you can think of the two imors substitution, that's bijective. And so using a substitution, we create a dynamical system, which is called a substitution shift. So one way you can think of it is you take a fixed point. If the substitution is primitive, okay, I should say that a substitution is primitive if in every substitution word, you see all letters. And today I will assume that it's primitive and there's absolutely no loss of generality, right? Because the Ellis semigroup of a non-primitive bijective substitution is just a disjoint union of the Ellis semigroups of its components, right? So we can safely assume that our substitutions are primitive. So I'll go back now to defining a substitution shift. You take a fixed point and you take the shift orbit closure of that fixed point. That will give you a space. If you prefer, another way to define the substitution shift is you look at all the words theta to the n of A, where A is a letter and n is a natural number, and you look at all the subwords that appear, that's your language, and your shift space is the space of all bi-infinite sequences, all of whose subwords belong to that language. Okay, and with the shift, the topology is 2 points are close if they agree on a large enough central block. Okay, so we have an invertible map, which is the shift, and it's continuous. Okay, so I leave this now. All right, so with Marcy Barge, last year, Johannes proved a very nice results. And so what they proved was the following. They said if you have a bijective substitution shift, so start off with a bijective substitution of length L, then its Ellis semigroup is the kernel union with the action. So Z here represents all powers of the shift, all right? And what they showed is that there's nothing else, okay? It's just the kernel union, the shift action, okay? So now we know the kernel is completely simple, okay? Because it's a kernel, but also because of the Ellis-Nakamura lemmas, which tell us that we have, for sure, we have idempotence. So natural question then is, what is the Rees semigroup representation of this kernel M of x theta, right? I can write it as a matrix semigroup, and this is what Johannes and I did last year and this year. So I'm going to not define some things now. I'm going to then go back and describe what these objects are. So if you give me a substitution theta, we find two groups, finite, so we call them G theta and gamma theta. G theta is called the structure group, and gamma theta is the little structure group. We find a finite set I, also depends on theta, such that the great majority of substitutions live in the first bullet point, okay? So we define a notion called generalized height, okay? And if you don't know what it is, actually you won't know what it is because we define it, but if you don't know what height is, what classical height is, like as defined by Decking, don't worry about it. But most substitutions have trivial generalized height, and then we describe their kernel as the following matrix semigroup. Okay, I theta is this set which I will define. It indexes the right ideals, plus minus indexes the left ideals. So the plus and the minus just tells you, are you taking the limit as nk tends to positive infinity or nk tends to negative infinity? And the important thing is the structure group. So here the structure group is going to be G theta, this one of these groups, to the power of the L-adic integers, semi-direct product with the L-adic integers. Okay, so I'll show you how you get this. What happens in the other case is if you have a generalized height H, and I'll define this in a minute, that's where the small structure group gamma theta comes in. All right, so once again, we still have a Rees representation. This group G is a little bit different, okay? It's the normal closure of gamma theta to the ZL, semi-direct with Z mod HZ, semi-direct with ZL, okay? So it should be clear that these systems are not tame because G has cardinality 2 to the aleph naught, and then you're taking the matrix semigroup on G. Okay, but nevertheless, even if they're grotesquely huge, they have a very simple description algebraically, not topologically, but algebraically. Okay, so now I'd like to talk about how I would begin to get such a thing, and I'll give you the background on the next slide, but then I'll focus on the 2 imors substitution. Okay, so what is our proof technique? So it's as follows. There's a notion of recognizability for substitutions, okay? So what this means is if you give me a point X in my substitution shift, I can uniquely desubstitute, okay, with any power of theta. So in particular, if you give me a natural number N, I can find a Y, a unique Y in X theta, and I can find a shift K between 0 and L to the N, such that I can write X as the kth shift of theta to the N of Y. So I can do this for every N, and what this means is I can actually define a factor map from my substitutions shift into the L-adic integers. So how do I do that? If I want to find the first N digits of pi of X, okay, I take X, I desubstitute it with theta to the N, as I have here. I find a K, and I take the base N expansion of that K, and that will give me the first N digits of pi of X. And I do this for every N, all right? And an important point here is what is a d-substitution of a fixed point? Well, if I have a fixed point x, then x is equal to theta of x. So k is always 0 for any n, right? So if k is 0 for any n, then the image of a fixed point in the L-adic integers is 0. Okay, so this map pi, which is a factor map between dynamical systems, this is a group rotation ZL plus 1. Okay. So the map pi defines a semigroup morphism from the Ellis semigroup of x theta into the Ellis semigroup of the rotation on ZL. All right. So that's pi tilde here. It's a semigroup morphism. Now, I said earlier that Ellis semigroups of rotations are very simple. In fact, they're algebraically isomorphic to the group itself. All right. So I have a sequence from the Ellis semigroup of x theta into the L-adic integers, and this pi tilde is definitely not injective. It has a huge kernel, and this kernel we call E-fib. Right. So the reason why we call it E-fib, it's the fibered semigroup, is because it's the set of elements in my semigroup. All right, so I should back up here. So this factor map pi, it enables me to look at my substitution shift space x theta as a fibered product. All right, so it lives over the L-adic integers. And for every element in my L-adic integers, I have a fiber. I have a bunch of points in x theta which project onto z. Okay, so for example, here is 0. I told you that where the fixed points are belong to the fiber above 0. Okay, and E-fib, which is the fibered semigroup, basically functions in E-fib. They can shuffle points or project points in fibers, but they cannot move points from one fiber to another. All right, and the important thing here is that idempotents belong to E-fib. Okay, so why is that true? Well, if it's an idempotent, it means E equals E squared. Now, pi tilde is a semigroup morphism, so I have pi tilde of E is 2 pi tilde of E. So all idempotents will belong to this E-fib. So E-fib is very important, and we spent much of last year just working with E-fib. Okay. So now I want to focus on two imors, okay? And I would like to prove the theorem. I need to know, to get the Rees matrix representation, semigroup representation, I need to know what the idempotents are. All right, so how am I going to do that? So I'm going to do that with proximality, right? I said that if I have pairs of proximal points, I can guarantee existence of idempotents, so let's do that. So remember, x and y are proximal if they agree more and more if you move off to positive infinity or negative infinity along the sequence. Okay, so let's look at the two imors substitution, and let's find examples of points which are right proximal or left proximal. So there are 4 fixed points for two imors, right? And I'm going to label them as here. So A dot A is the fixed point that I get from the seed AA. And as an example, the 2 fixed points AA and BA are right proximal. In fact, they're right asymptotic. They agree from the index 0 on. Okay. Another example is AB and BB. Those are right proximal. I can also look at left proximality. Okay, so here I have 4 pairs of proximal points. Okay, and now the general theory guarantees me, because my substitutions are primitive, the shift acts minimally, they guarantee me that for every pair of these proximal points, there's an idempotent which sends one to the other. Okay, so in principle, there could be 8 of them then, 8 idempotents. Okay, so now let's see what happens. So I have in this picture, AA is a fixed point and BA is a fixed point, and this is a right proximal pair. And so I'm guaranteed the existence of a minimal idempotent P, which sends AA into BA and which fixes BA, right? I'm also guaranteed a minimal idempotent P tilde, which sends BB onto AB, right? But it turns out that those two idempotents are exactly the same, all right? And this is where bijectivity is, one of the places where bijectivity is used. Why is that? So why is P equal to P tilde? So to define P, I have to take a limit of shifts, sigma to the nk, right? So here's AA and here's BA, and I've just drawn the right half. They agree on the right. So to find a map which sends AA to BA and BA to BA, I just need to take a limit. So this arrow here is where I've moved my radix point, all right? I just need to take shifts so that if I put my radix point here, I see theta to the n of B on the left and theta to the n of A on the right, all right? For arbitrarily large n, I let the sequence go to infinity, I'll hit my idempotent. But now what happens if I move the shift on the right fixed point starting with A so that I land here, what happens to A dot B and B dot B? Well, because of bijectivity, the shift will land precisely at exactly, it will see theta to the NA on the left and theta to the MB on the right, okay? So this means that as soon as I send AA into BA, I'm guaranteed to send BB into AB, okay? So now I know exactly what this idempotent P, which exists, does to my 4 fixed points, but what else, what does it do everywhere else, okay? All right, so what it does everywhere else is very simple, right? So there's this, it's not too hard to show that if you have bijective substitution, the only way a pair of points can be proximal is if they're in the shift orbit of one of the fixed points, or 2 of the fixed points, okay? So otherwise, it's just everything else, they're definitely not proximal, no other pair, all right? So this is telling me, and then we had another fact that I put on earlier on, this general theory that X and Y are proximal if and only if there exists a minimal idempotent P such that P of X equals P of Y, okay? So you can sit down with a pencil and in about 2 lines, you can show that if I have a point X, which is not proximal to anything, okay, then any minimal idempotent must fix X, right? And so sort of to summarize here, the minimal idempotents collapse fixed points and they leave everything else that's not in the orbit of the fixed points fixed, okay? All right, so now we can finish off 2 imors. I said originally that there could be 8 idempotents, but there are in fact only 4 because of these conspiracies, okay? And you can just list them, all right? So I think this is the one we found earlier. I can look at other proximal pairs and each time get an idempotent, okay? And as I said, these idempotents fix everything else. So instead of looking at the fibered Ellis semigroup, so the part of the Ellis semigroup which fixes fibers over ZL, actually I just have to focus on the restriction of that fibered Ellis semigroup to the fiber over 0, which is just for the fixed points, okay? So, so that's what we define E naught fib. So that's a restriction of, remember, the parts of the Ellis semigroup which do not move across fibers, and I'm just restricting to the 0 fiber. So our theorem specific to 2 imors is the following. These 4 idempotents generate E naught fib without the identity. The identity map is always part of it, okay? So that's not trivial. And algebraically, I can tell you exactly the matrix semigroup representation of everything. So for example, the matrix semigroup representation of E fib restricted to the 0 fiber, well, that's going to be generated by these 4 idempotents. So it's M of the group G theta is S2. I'll define G theta in a minute. There are two ideals, right ideals, and this matrix A is something I will choose. Now, to pull that back up to the fibered Ellis semigroup, so instead of all things, which fix fibers, what I have to do is I take exactly the same semigroup representation, but I change the group. Instead of just G theta, which is S2, I take G theta to the power of Z2 quotiented out by Z, right? And now to pull up to the full Ellis semigroup, we take the fibered semigroup and we take a semi-direct product with the two adducts. So 2 because the length of the two imors substitution is 2. Okay. All right, so that gives you an idea of how you would do it. For bijective substitutions, we're very lucky. They're the only proximal pairs are amongst the fixed points. We look at them, we inspect what can be done, what can map to what, and what the conspiracies are. And then we can pull this back up to the full Ellis semigroup description. Except for this is not always the case. It is not always the case that the idempotents generate E naught fib without D. And I'll talk about that in a minute. But first I'm going to define G theta, gamma theta, and I theta. All right, so I know some of you in the audience know far more about substitutions than I do. So in fact, one of the reasons I wanted to talk about this gamma theta is because I've never seen it, and it would be curious to see if any of you have met it. All right. So these are the three objects that are needed to define the Rees matrix semigroup. Okay. So remember, my substitution is theta. I write it as theta naught dot 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 theta L minus 1. And now I think of the maps theta I, remember they're all bijections, so they belong to a permutation group. Okay. And the structure group is going to be the group, the structure group of theta G theta is the group generated by all these bijections. All right. It's R set, this is a set, not a group, is what I do is I take theta to the n at I minus 1 inverse, and I compose it with theta to the n at I. So you should think of this as sort of like the shift map, okay? Because if I'm in location I minus 1 and I want to shift to get to location I, what do? I have to first undo what I do at I minus 1, so I take an inverse. And then I have to do what I do at position I. Okay. All right, so now this is G theta. G theta, the structure group is a pretty natural object. It has shown up before. But the little structure group, gamma theta, is now, I define it to be the group generated by all expressions of the form GH inverse, where G and H belong to I theta. Okay. All right, so let's do an example for those three. If I go back to imors, G theta is going to be the group generated by all bijections theta to the n of I. Well, I've written the substitution like this now. It's much easier to see. You see here is the identity map, and here is the map which flips A and B. So G theta is S2, right? So that's why I had an S2 in my previous slide. I theta, you can also once again check that I theta is also going to be S2, all right, and therefore gamma theta bar is also going to be S2. Okay, so in this case, G theta equals gamma theta bar, and that's exactly when the idempotents generate the fibered semigroup. Okay. So our first result was that if G theta is equal to the normal closure of gamma theta, then the idempotents generate all the maps on E fib restricted to the 0 fiber, and I can describe the kernel of EX theta as this matrix semigroup. Okay, and in this description, there's no gamma theta. All right. Because gamma theta bar equals G theta. So no need for it. All right, so in fact, this is an if and only if. G theta equals gamma theta bar if and only if the idempotents generate the fibered semigroup. And of course, a natural question is, does it always happen? And the answer is no. And it's quite easy to create an example. So here, I'll show you what we've done. So this is a substitution on 3 letters. What we did was we put the identity in every other spot, okay? And then what we put in between, here we flip A with B, one transposition. Here we flip A with C, another transposition. And here we flip B with C, so that's a 3rd transposition. So therefore the group G theta, which is the group generated by all of these, since it contains all transpositions, is S3, all right? But because we put the identity in each place, in every other place, if you compute I theta, you will get the set of the 3 transpositions. And now to compute gamma theta, I have to take one of these followed by an inverse of another. And what I get are all even permutations. So I get A3, which is normal. So gamma, the normal closure of the little structure group is A3, which is not S3. So our previous theorem, my condition was G theta equals gamma theta bar. Well, that doesn't apply anymore, okay? And in this case, the idempotence will not generate the fibered Ellis semigroup restricted to that fiber. All right, so I can now define generalized height. What is generalized height? It turns out that G theta quotiented out by gamma theta bar is finite and cyclic, and its order is what we call the generalized height, okay? And most substitutions have trivial generalized height. So for most substitutions, G theta equals gamma theta bar. But I just want to comment here. So if you don't know what the height is, don't worry about it. But this is the classical definition of height, right? So it's the greatest common divisor, coprime to L, of all n such that U sub n equals U naught if I have a fixed point U, all right? So in our case, the generalized height is at least the classical height, but it can be larger. And the example I just showed you a minute ago, this is an example which has trivial height, because you see AA here, right? So it has trivial height, but it has non-trivial generalized height. Okay. So to finish off our algebraic description, what happens if you have generalized height? Well, generalized height H, well, it's not as beautiful as the trivial height case, because we don't always get an explicit description. But the EFib, so the fibered semigroup restricted to the fixed points, is exactly as it was before. And it's the structure group G theta, which is there. We can have an explicit matrix semigroup for the fibered Ellis semigroup without the identity. But we can only give you an explicit description if we assume that the structure group has an element of order H. So then G fib, the structure group here, is going to be normal closure of gamma theta to the power of L adix mod Z semigroup with the height, Z mod HZ. And the actual Ellis semigroup, you can describe it implicitly, from this short exact sequence, right? And we can actually describe it as a semi-direct product if the generalized height equals the classical height, which is not always the case, okay? But which is the case in the great majority of things. All right, so that's our results. So now everything I've talked about is describing the Ellis semigroup algebraically. All right, so we have a almost complete algebraic description. But of course, the Ellis semigroup is also a topological object. All right, so you can talk about a topological description. And that is much more complicated. In particular, we have a topological description of the fibered Ellis semigroup. So the set of all functions in my Ellis semigroup which don't move fibers, right? And here it is. So E fib is topologically isomorphic to What you see here is just the matrix semigroup you saw before, and that's what lives over the 0 fiber. It's exactly what we had before. And in the rest of my space, I have a big Cartesian product. Okay, on the other fibers, the only way the Ellis semigroup, the fibered Ellis semigroup can act is with bijections generated by the structure group G theta. All right. And if, so that happens if the generalized height is trivial, and if it's not, then you have the same kind of description, but instead of the structure group, I have to take the normal closure of the structure group, which is going to act on the non-zero fibers. Okay, so that is the topological description. So to summarize, both descriptions are very explicit and actually very sort of simple to state. All right, so I'd like to finish off by saying what next. So usually what you can do for some substitutions, you can probably do for most substitutions. Maybe the answer is not as nice, but I just want to sort of point out that we've used bijectivity in many places, and we need sort of tools to get rid of these, to get rid of this assumption in different ways, all right? So I'm going to remind you that this result by Johannes and Marcy Barge, that the Ellis semigroup is the kernel union the action, that's only true for bijective substitutions, all right? In general, bijective substitutions, the proximal pairs only lived amongst the fixed points, but in general, they could be uncountably many proximal pairs, which means that there's a lot more work to do to control the conspiracies, both between idempotents and also across the fibers, all right? And so that's where we're at, and how do we deal with that? Okay, thank you very much. That is the end of my talk.